Hi, today I'm going to explain about gas absorption tray tower or tray column. Are you ready? Okay. Let's look at the tray tower diagram. As what we can see here, we are dealing with the countercurrent contacting gas and liquid. So our gas is fed at the bottom of the column and liquid is fed at the top of the column. This is the general configuration of the tray tower. As what we can see here, the liquid and the gas will be in contact to each other in the column, and the contacts occur on the tray. Liquid flows parallel to the tray. As you can see here, this is where the liquid will flow and the gas flow perpendicular to the tray. So normally, types of tray used in the tray tower is sieve tray, bubble cap tray, and valve tray. There are two types of column that's involved in the design. One is called absorber, the other one is called stripper. For both design of the column, we need to determine the theoretical stages of the column. Both absorber and stripper have different application and different operating condition. For the tray tower, there are two inlet stream, which is feed gas stream and solvent stream, and two exit stream. One is called extract stream, the other one is called raffinate stream. So the raffinate stream is the gas stream, extract stream is a liquid stream. So we have two liquid stream, which is called extract and solvent, and we have two vapor stream, which is called feed gas and raffinate. The feed gas consists of solute, and this is the feed gas that we want to treat. Majority of the solute in the feed gas will be soluble in the solvent and collected at a extract stream, where the rest of the solute and very minimum of the solute will be released at the raffinate. This is how the sieve tray looks like. You can see there are many small holes to allow the vapor to go through perpendicular to the tray, and we have majority or most of the liquid will flow parallel to the tray. So this is a bubble cap tray, valve tray. The following are the design criteria of the gas absorption column. The operating parameter for the absorber are pressure and temperature. Normally, the operating pressure in the absorber normally very high, but the operating temperature for the absorber is normally at room temperature. In the design, we need to minimize the stage requirement or the tray requirement or for the absorbent flow rate. Next, we need to lower the equipment volume required to accommodate the gas flow. Most absorbers are operated at feed gas pressure. Sometimes it is greater than the ambient pressure and temperature. Therefore, absorbers should be operated at pressure or temperature that would not condense the feed gas. Now, let's look at the design column for the stripper. The stripper operating parameter is pressure, and normally the pressure used is very low. And the operating temperature for the stripper is very high. The design is to make sure that we can minimize the stage requirement or absorbent flow rates. Common strippers are operated at pressure just above the ambient pressure and temperature. High temperature can be used, but it should be not so high as to cause undesirable chemical reaction. And the operating pressure and temperature must be compatible with the necessary phase condition of the stream being contacted. This operating condition is opposite than what we have for the absorber. Therefore, strippers should be operated at pressure or temperature that would not vaporize the feed liquid. These are the steps involved in order to calculate the theoretical stages for the absorption column. Before we can determine the number of theoretical stages for the absorption column, we need to determine equilibrium line and operating line for the given case. We are going to solve it using graphical method. Now, let's label the stream of the absorption column. The feed gas stream is labeled as Vn plus 1. The extract is labeled as Ln. The solvent is labeled as L0. And the raffinate is labeled as V1. To draw the operating line, we need to have two coordinates. The value that we need to determine the coordinate is the y value from the feed gas, which is y(an) plus 1. Next is x(an). From V1, we need y(a1), and from L0, we need x(a0). So A is the solute for the given mixture of gas. So this will give us the bottom coordinates and the top coordinates. We might want to use the material balance to solve the problems. We might want to use the overall mass balance, or maybe mass balance on component A. To plot the operating line, we need two coordinates, and that coordinates come from x(an) with y an plus 1 to give you one coordinates, and the other coordinates come from the solvent, which is x a naught and y a1. Alright, so you have to know that your feed gas normally consists of the solute that you would like to remove, and you can call the solute is A. So the components that you have here, the mole fraction that you have here, comes from the solute, which is YAN plus 1. And you also have another component which is also called carrier. Normally it is air, and it is labeled as YBN plus 1. In the neighboring stream, the extract stream that we have, so the extract majority consists of the solute, which is XAN, and it consists of majority of the solvent that you use, which is XCN. Solvent used in the process normally pure solvent. If it is pure, it is only consists of the solvent, which is X C naught. But sometimes it is not a pure solvent. It consists of solute in the solvent, so therefore you have X A naught. For the raffinate stream, we have all the air will be released at the raffinate, so therefore YB1. And then we also have some of the solute at a very minimum concentration or mole fraction will be released at the raffinate. So we can label that as YA1. But remember, to get the operating line, we just need to have YAN plus 1, XAN, XA naught, and YA1. So this is our main concern in the calculation, so that we can plot the 2 points and connected the 2 points to get the straight line. The location of the operating line depends on the types of absorption column that we have. So if we were to have absorption column, we're going to have operating line here before we can see the equilibrium line. If we were to have stripping column, then we can see that the operating line lies below the equilibrium line. So the location of the operating line will be different if we were to use absorption column or stripping column. So this is the graphical method used in order to calculate the tray number of the tray column, or sometimes you call it to calculate number of stages in the column. For the gas absorption column or absorber that we are dealing here, the top points here comes from the bottom point, and here comes from the top point. So if we were to label the coordinates, so this would be the coordinates for X, AN, and Y, AN plus 1. So you get this coordinate, and the other coordinate that you get for the operating line is from X A0 and Y A1. So these will be the two coordinates. When you draw a straight line to connect both points, you'll get operating line. So you start to draw graphically on to find the number of trays. You start from the bottom point, draw horizontal line, vertical, vertical again, vertical again, and horizontal, and then vertical again until you meet the end point of XAN. So to calculate this, you just calculate the horizontal line 1, 2, 3, 4. So there are 4 stages for this tray tower for the gas absorption column. So that is how you calculate or you design the number of stages or theoretical stages for this column.